All right. So you see the word bioenergetics and you're probably like, not more glycolysis, not more crabs, not more electron transport chain. But luckily, we're not talking about that today. Today, it's more about how we get calories out of food, or even more specifically, what exactly is a calorie, right? So a calorie, what I want you to know is that it's just a unit of measure. At the end of the day, a calorie is a calorie. It is a unit of measure, just like a degree Fahrenheit. I'm pointing outside, you can't tell. A degree Fahrenheit is a degree Fahrenheit, right? It is a measure of energy. Same thing here. A calorie is the measure of energy that it requires to raise the temperature of 1 kilogram of water 1 degree Celsius, right? So it is just a unit of energy. So we have ways that we can measure the relative energy or the relative calorie content of a food molecule. One of those ways is a bomb calorimeter. Many of you guys have heard of bomb calorimeters if you've been in biology or chemistry or whatever. Essentially what it is a self-contained system where we actually heat an element. So we actually heat up something like a food sample and we check to see how much heat is produced whenever that chemical or that food stuff is burned. I've done this before. It's a really cool concept. It's really freaking simple at the end of the day too. And what's crazy is, let's say that we want to test a full day's worth of energy. How do you think we do that? We literally put all that food in a blender, close the blender, blend that sucker right up, put a couple of it into like little sample containers, send it off to a company, and that company then puts it into a bomb calorimeter and tells you exactly how much energy is associated with that day's worth of food. Really kind of a cool process, but as you can see, kind of takes a lot for granted and it kind of misses a lot of steps in there. So what does the heat of combustion, or what is the kilocalorie, what does the calorie measure of foods look like? If you look at this graph, or it's not a graph, if you look at this text, then you'll notice that some of these don't exactly look like the numbers that you would see on the back of a nutrition facts label, where 1 gram of carbohydrate is equal to 4 calories, 1 gram of protein is equal to 4 calories, and 1 gram of lipid is equal to 9 calories. What you notice is that they're quite a bit different, right? 1 gram of carb actually releases 4.2 kilocalories. 1 gram of protein releases 5.65, and 1 gram of lipid releases 9.45. So some of them are more off than others. Carbs is pretty accurate. It's pretty different than what we would normally expect to see. So the heat of combustion is a little bit different for carbohydrates than it is for lipid, than it is for protein, right? I don't want you guys to get into the minutia of this. Just view it from a 30,000 foot view. The major reason why there is a dramatic difference between protein, right? Lipids a little bit different. Protein is dramatically different, right? 4 kcals normally when we're thinking about it on nutrition facts, 5.65 whenever we put it into a bomb calorimeter. The reason is twofold. It is protein type as well as the nitrogen content. So the nitrogen content is going to drive the difference in combustion. But what does that look like when we actually put it into the body? Things change when we put things into the body, right? We're going to actually have more of a normal looking value level. And this is going to be called our Atwater values. For the rest of class, this is what we're going to be focused on using. Anytime we're calculating energy demands, anytime we're calculating anything, we're going to be focused on Atwater values. I just want you to know that there is a little bit of a difference in real life compared to what happens inside of the body. So those Atwater values, carbohydrates are 4 calories per gram. Kcal is the normal denotation, kilocalorie. Lipid is 9. I'm trying to rapidly do my fingers here. And then protein is 4 calories per gram. So those are the ones that you really need to know. Now, what I want to have a discussion of is a calorie being a calorie always. Is a calorie always a calorie? And I want you to stop, hit pause, think about it. Is a calorie always a calorie? I think that yes, a calorie is always a calorie. Personally, selfishly, scientifically, a calorie is always a calorie. And the reason I say a calorie is always a calorie, all calories are the same, is simply because calorie is just a unit of measure. So outside of the body, this calorie is representing a potential energy, basically, right? Every calorie has a potential amount of energy associated with it. So if we have a calorie of broccoli or a calorie of peanut butter or 100 calories and 100 calories or 1,000 calories and 1,000 calories, outside the body, those calories are all the same. When things change is when we introduce it into the human body, into a different system, right? What I want you to think about is a human body a closed system exactly like that bomb calorimeter? Or is it a isolated system exactly like that bomb calorimeter? And the answer is no, right? We have an exchange of energy. We have an exchange of matter. We eat food from the external environment, and that matter makes it into us. We take and we pull energy from a system. We pull heat. If you touch a hot stove, you get heat deliverance to your hand. We have these exchanges of heat and energy or energy and matter happen all the time. A closed system just has an exchange of energy where we could heat something up, but there's no change of matter, right? We have a change of matter because we consume food and because we pull nutrients out of that food, we are actually consuming matter. So we're actually an open system. All of the laws of thermodynamics apply to non-open systems, closed or isolated. When you have an open system, you start to violate many of the laws of thermodynamics. It's not that they don't apply, it's just that there's a different level of accuracy that's involved here. So if we eat food, let's say we eat this hamburger, what are we going to do with it? We're going to digest it, we're going to absorb it, and we're going to get the fats, carbs, and proteins that are coming from that energy, from that matter. We'll be able to make kinetic energy off of it, but we're also going to be able to dissipate heat as a response from that, and we're going to produce carbon dioxide and water as we're making energy from that macromolecule. So there's a bunch of stuff going on such that each calorie that we consume is going to affect us different, right? Every food source that we consume is going to affect us different. What happens if we consume a high fiber item? Are we going to be able to just get massive amounts of kinetic energy from that or produce massive amounts of heat? No, we're going to produce massive amounts of gas and we're going to fart, but we're not going to produce a ton of kinetic energy. We're not going to be able to actually pull what we need out of it because we don't have the necessary enzymes to pull what we need out of it. Regardless, there's still a calorie density associated with that high fiber food because it's outside the system when it has that calorie association with it. Does that make sense? So a calorie is always a calorie until it is not. Until it is inside of the human system, things change. This is why a calorie of carb is not the same as a calorie of fat inside of the human system. So if we talked on the last slide about mechanical work and energy creation and blah, 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 very indirectly, very, very quickly, what are we trying to do when we measure energy expenditure? Well, we're trying to measure the approximate caloric need for that energy expenditure. And how we do that is either through direct or indirect calorimetry. So this is essentially a measurement of heat transfer, a measurement of combustion and the change of heat as it goes. The next couple slides, we're going to talk about we'll have one slide on direct measure, and then we'll have a couple of slides on indirect measures and how we can actually use those in physiology, in exercise science. So the first one is a direct calorimeter. This is a human calorimeter or a metabolic chamber. What's going on in a metabolic chamber is we have essentially a thermometer up here in the top left that we're collecting heat loss from the human body inside of this closed system, this isolated system. I guess it's technically a closed system, right? Because we have a change of energy, and that energy is going to be producing a change in the thermometer. So this is basically just turning a human into the center of a bomb calorimeter. That heating element is the human. So we can actually measure all of the heat production that human creates. When we're able to measure the heat production, we can see what the caloric need of that exercise is. So in metabolic chamber studies, we will actually take and lock people in these rooms for prolonged periods of time, and we'll see how much their metabolism changes, how much their energy expenditure changes with variations in food type and variations in exercise type, exercise duration, all that type of stuff. Now, just from looking at this, you can probably assume this is a pretty complex and expensive piece of equipment. Realistically, these studies aren't done often. They're very hard to come by. They're very expensive, and this piece of equipment is crazy expensive and crazy rare. These are not just found everywhere. So what we need to do is we need to start going in an indirect route. So what we're doing with an indirect route is we're measuring the changes in oxygen and we're measuring the changes in carbon dioxide. If we're consuming oxygen whenever we're having a energy releasing reaction and we're producing carbon dioxide, we can actually measure the ratio of oxygen and carbon dioxide to be able to take a pretty solid guesstimate of what sort of fuel we're actually burning. A couple different ways that we can do this. We can use spirometry. We can also use this thing's called a Douglas bag. It's really funny to watch individuals that historically used Douglas bags. So you used to breathe through a mask into a tube that was collected into like a Mylar bag, essentially. And there's pictures of individuals riding a bike behind someone running. And as they're riding a bike, they have like bags all over them. They're just full of air and it looks like the most inefficient thing ever. And I kind of just think this guy looks like a bouse, right? Like he's boxing in the middle of the heat of summer with a mask and a bag attached to him. He kind of looks like Bane. Then we have a ventilated hood technique. This is what we're going to be doing for RMRs, resting metabolic rates for the most part. Double labeled water, we're not really going to talk about. It involves a lot of chemistry. And truthfully, while it's really a gold standard for indirect calorimetry, it's not used as often. So let's talk a little bit about this spirometry. So when we breathe out, we actually produce something called a respiratory quotient, or we can calculate something called a respiratory quotient. And what a respiratory quotient, or an RQ, is it's the ratio of carbon dioxide produced to the oxygen consumed. Now, if you remember, when we jump from pyruvate to acetyl-CoA, as we're transitioning from glycolysis to Krebs, we're actually going to be losing a carbon, and we're going to be producing carbon dioxide. So if we're going from fat to acetyl-CoA, we're not going to be producing the same amount of carbon dioxide. So the concept basically goes that if we're burning higher levels of carbohydrate, we will be producing significantly more carbon dioxide. If we're burning lower levels of carbohydrate, we'll be producing less levels of carbon dioxide. So the respiratory quotient will scale up the more that we're using carbohydrate, and it'll scale down the more that we're using fat. So the RQ, this kind of standard set RQ for carbohydrate, where we're burning 100% carbohydrate, is 1.0. So 1.0 for an RQ means we're burning 100% carbohydrate. An RQ of 0.7 means that we're burning 100% fat. So an RQ of 0.7 means we're burning 100% fat. An RQ of 1.0 means we're burning 100% carbohydrate. That would mean that a 0.85 RQ would be a perfect blending of 50-50 carbohydrate and fat. Now, there is an RQ associated with protein, but because it's 0.82, it kind of gets pushed out. It kind of gets lost in the noise. And the goal is that our protein use is negligible. We want to be using as little protein as possible, remember? So we kind of just assume that that is going to be a 0. And we kind of mainly rely on what's going on with the ratios between carbohydrate and fat. The RQ is going to vary based on how an individual is eating. If an individual is eating a slightly higher carbohydrate diet or a mixed diet of about 40% carb, 60% lipid, that RQ is actually going to scale up. So at rest, they're not going to be burning 100% fat because they're not consuming 100% fat. Where this actually gets really cool and where this actually changes a little bit is individuals that are following something like a ketogenic diet, right? They're burning and they're consuming so much fat that their RQ is literally 0.7 because they are exclusively reliant on fat stores for energy while they're at rest. So the resting RQ of an individual on a low carb, high fat diet is very close to, if not 100% fat, or 0.7. Individuals consuming a mixed diet, that'll actually ramp up to somewhere in that 0.78, 0.82, 0.84-ish range, where they're actually at rest burning a pretty clean mixture of fuels for both carbohydrate and fat. If the RQ is what's happening during rest, we can still measure the respiratory exchanges of gases of carbon dioxide and oxygen during exercise, right? We can still put a mask on someone who can still exercise them. While it sucks, it's still doable. And what we can then measure is something called a respiratory exchange ratio. And so the respiratory exchange ratio is what's occurring while we're exercising. And as we change in exercise intensity, we're going to change how much carbohydrate and fat we're fueling with, right? So as we increase intensity, we're going to increase the amount of carbohydrate that we're burning. If we're increasing the amount of carbohydrate that we're burning, we're going to be increasing our RER, such that when our body is at a very high intensity of exercise and we're burning 100% of carbohydrate, because we're at a high intensity, our RER is actually going to be 1, right? Does that make sense? So as we increase in intensity of exercise, we're able to see an increase in carbohydrate oxidation, in carbohydrate utilization, and the intensity of exercise actually tracks with the carbon dioxide production. So if we're working at a low intensity exercise, our RER is going to be a little bit lower. If we're working at a high intensity of exercise, our RER is actually going to be significantly higher. It's kind of neat. And just like we talked about in the last lecture, as we increase in training status, we increase our ability to burn fat, we increase our mitochondrial biogenesis and our mitochondrial density and our capillary density. So it makes sense that as we get more and more fit, we get better and better at burning fat and use less carb at each intensity. So it would seem that as we get better and better trained, we actually have lower RERs at each work rate because we're using less carbohydrate. We're using more fat. So we're able to drive our RER a little bit lower. It's really a neat concept, and we can track these changes just by measuring the breath of someone. And these changes change. Each one of these things changes based on the diet that someone's habitually consuming. So if it's a low carb, high fat, their RER is going to be driven a little bit lower. If it's a high carb, low fat, their RER is going to be driven a little bit higher. It scales with how we're burning fuel. It's a really neat process. We've already talked about this, so I'm not really going to dive too much further into this graph. Just as we increase in intensity, we increase in carbohydrate utilization, we increase in fast anaerobic intensity type measures and anaerobic energy systems. As we continue on for long-term energy, it's going to be that aerobic system, and there is that intermediate kind of mixed fueling, glycolytic-ish range as well. If we're able to measure these changes in RER and we're able to estimate the changes in fueling coming from carbohydrates and fat, then that means that we're able to estimate the energy expenditure of an individual, right? We're able to estimate about how many calories an individual is burning, whether it's during activity, it's during rest, it's during maximal exercise, whatever. We can actually estimate kind of how much energy is associated with that person at that time. Now, I'm not talking about like this like healing crystals and kind of witchy woman, Wiccan type concept of energy, right? I simply mean caloric expenditure, combustion, or heat production. So there's a couple of different things that we do, and a big one that we're going to be looking at is total daily energy expenditure. How many calories is a person burning across an entire day? We can have energy associated with each activity, energy associations for exercise, energy associations for digesting a food. Each one of those is going to play a role in how much energy an individual burns. A good, clean picture is how much energy an individual burns in a day, because it's a set time frame for each individual, right? Every single person that is alive experiences 24 hours a day. So we can kind of divide through by a common denominator of 24 hours and see what does the total daily energy expenditure look like. There's more than just what happens when we're at rest, right? Like right now, as you're listening to me, you're probably hating your life in some way, shape, or form, but you're also probably at rest. Some of you might be driving and listening to this. Some of you might be sitting in your dorms listening to this and watching the video. Some of you might be exercising. Each one of you are doing something a little bit different. If you're at rest, if you're laying in bed listening to this, then we're going to be measuring your basal metabolic rate. If we had a mask on you and we were measuring your carbon dioxide and oxygen exchange, right? That basal metabolic rate is how many calories it would cost or it would burn in your body. Your body would burn. Good Lord, we got there. How many calories your body would burn if you were to not do anything all day, if you were to not get out of bed at all, right? That's your basal metabolic rate. How many calories does your body need to sustain life with no energy really being needed, right? Like no muscular contraction, no movement like I'm doing right now. That makes up about 70% of your total daily energy expenditure because your body just has to be alive, right? That next step up, this NEAT, is pretty neat. Jokes. I'm out of dad jokes today. I'm sorry. This is non-exercise activity thermogenesis. So this is how much energy your body produces doing non-exercise activities. So there's a difference between physical activity and exercise. Exercise is planned, dedicated physical activity. Physical activity is unplanned movement and skeletal muscle movement and contraction, right? So like the type of stuff that I'm doing right now is I'm talking, I'm moving my hands, I'm kind of bebopping around in this chair. That's non-exercise activity thermogenesis. So this is all muscle contraction that's occurring above what I need just to stay alive and not get out of bed all day. Walking across the campus trying to go to class, walking upstairs, all of that type of stuff is non-exercise activity thermogenesis. And if you look, it actually makes up a pretty big chunk of how many calories we burn in a day. It's about 15% of how many calories we burn in a day. Next one up is TEF, or thermic effect of food. If you remember, each one of those macronutrients we've talked about has a different digestion process and a different absorption process. Each one of them also has a different energy associated with it. Protein, believe it or not, has the highest thermic effect. While it doesn't have the highest caloric association, it has the highest thermic effect. It actually heats our body up. The combustion process heats our body up the most and takes the most calories to digest, absorb, and use that protein. So it's got the highest thermic effect. So depending on how we adjust and manipulate our diet, we can actually adjust how many calories we burn in a day. That next one up is exercise-associated thermogenesis, or exercise activity thermogenesis. This is how much energy we burn from exercise. For the gross majority of us, we spend very little time, if any, doing exercise throughout the day. So it would make sense that this is only a very small percentage of our total daily energy expenditure. If you're one of those crazy folks that goes out and actually enjoys running, like who are you? I'd rather lift weights. Then you might kind of increase this more away from that like 5 to 7%. If you run ultra marathons, you're going to spend a greater percentage of your day exercising than you are the average individual, like most of us, right? So that exercise activity thermogenesis kind of scales, but for the most part, it's not really associated with high levels of energy expenditure. It's very small and acute. Believe it or not, there is actually a biological difference between men and women when it comes to basal metabolic rate. On average, men burn about 10% more calories throughout the day. Our total daily energy expenditure for men is a little bit higher than women. This is kind of the reason why we see those memes or funny pictures floating around the internet that focus on how much easier it is for weight loss to occur in men than in women. Don't know exactly why. It's probably a hormonal based reason. It could also be a muscle mass type reason. The more muscle mass you have, the significantly greater your basal metabolic rate is going to be. So if you want to, side note, if you want to lose weight, one of the best ways to do it is actually increase your muscle mass. So that means lift weights and lift heavy weights. So men and women are actually biologically different when it comes to energy expenditure, to circle all the way back. There's a bunch of different things that affect thermogenesis. There's a bunch of different things that affect energy expenditure, right? Muscle mass is one. Physical activity level. The more physically active you can be, the greater your total daily energy expenditure is actually going to be. So the higher your physical activity, the higher your energy needs are going to be. So you're actually going to produce more energy. This is kind of that theory behind 10,000 steps. For any one of you guys that track your steps every day, this is kind of that concept behind the 10,000 steps a day. The type of food that you're ingesting, so the higher the protein, you're going to be able to scale that up a little bit more. The climate, if you're in a hot, humid environment, that subtropical climate, you're going to have to work harder to maintain core body temperature. So you're actually going to have a higher energy expenditure. And then pregnancy, believe it or not, pregnancy is going to dramatically increase the amount of energy that an individual needs or is producing, their total daily energy expenditure. It makes sense because you're growing a baby, right? It makes sense. This is why the caloric needs of pregnant women actually increase during the time of pregnancy. It's a really neat thing. Something else that dramatically affects human energy expenditure is going to be the volume of training that we're subjecting it to. So, sorry guys. The higher the volume of training, the significantly higher the thermic effect of it is going to be. The significantly higher the total daily energy expenditure is going to be. the higher the volume of training, the higher the energy expenditure is going to be. It will dramatically increase the total daily energy expenditure here. Like if you look between these two bars, during a high volume period of time, you're almost 1,000 calories more per day. You need almost 1,000 calories more per day. That is wild. That's some of the reason why when it comes to, I think next week we'll talk about it, when it comes to the need for athletes to consume greater and greater amounts of calories, and sometimes the need for athletes to start consuming things like protein powder, even though they're typically not the most recommended, they have higher nutrition needs, so they need more energy, right?